In this video, we're going to talk about the Lewis-Randall rule and derive it. And this is useful for modeling the mixture fugacity of components. So we've talked about fugacities for pure components. Now we're going to talk about how that changes when you introduce multiple components in a mixture. So let's start by recalling how we defined fugacity in the first place. This is the mathematical definition of fugacity. It's the change in molar Gibbs free energy is equal to RT d ln of F. This is also something that we derived in a previous class. Well, not derived, but we defined it based on an analogy to what the ideal case was and what the deviation of fugacity was for a real solution versus an ideal solution. So for a mixture, what we're going to do is change this definition only slightly to make it the partial derivative of the chemical potential. The change in the chemical potential is equal to RT d ln, and then F caret, or F hat is how I'll usually refer to it, is a new definition where F hat of species I is the mixture fugacity of component I. So this is similar to a partial molar property where with this caret symbol just differentiates the mixture fugacity from the pure component fugacity. These are in general different things, but it's not, we use a hat here and not an overbar because it is not a partial molar property. The two are a little bit different. Okay, so the next step in this derivation is you're going to integrate this expression from x is equal to 1, which is a pure component I, to some mixture composition x. I'm just going to write that. So what does that look like for this expression? I'm going to add my bounds of integration here. So I'm going to integrate d chemical potential of species I from chemical potential for species I at some temperature, pressure, and x is equal to 1 to mu I Tp x equals the integral of RT d ln of mixture fugacity of component I, and my bounds of integration here are ln fi at Tp and x is equal to 1, and ln of fi at Tp and x. Now, a simplification that I can make here is that the mixture fugacity of component I, if xi is equal to 1. So actually, yeah, I don't want to confuse things. For clarity, I was thinking about putting a subscript I for all these x's. But if it's a binary mixture, we can, remember, set the composition of the entire mixture just by setting the mole fraction of one of the components, since the other one is set by the physical constraint that they're equal to 1. So I'm just going to leave it for clarity. But what I wanted to do was, instead of calling this the ln of the mixture fugacity of component I if x is equal to 1, this is just ln of fi at Tp. All right, because if x is equal to 1, there is no mixture. Therefore, it's the pure component fugacity, not the mixture fugacity. All right, now we will perform the integration, and in both cases, it's a simple integration for the most part because there are no function of the independent variable. So this RT can come outside of the integral. We've got nothing inside the integral on the left-hand side. So it's just mu I Tp and x minus mu I Tp and x is equal to 1 is equal to RT. And then since we have an ln of the mixture fugacity, when I subtract them, I can use a property of logarithms to put them in a fraction together. So it's ln of the mixture fugacity as a function of Tp and x divided by the pure component fugacity as a function of T and P. All right, now because this is confusing to have the chemical potential has the same symbol, regardless of whether or not it's a mixture property or not. So let's go back a second and say that we can, remember how we defined the chemical potential. Chemical potential is also known as partial molar Gibbs free energy. So recall chemical potential is also known as partial molar Gibbs free energy. To be quite honest with you, I don't know why they go through making a different symbol. I don't know why we can't just call it partial molar Gibbs free energy. There's probably a reason for that. I'm not sure why that is. But the idea here is that we're going to just simply replace this with partial molar Gibbs free energy. And then for chemical potential of a pure component, well, that is equal to the partial molar Gibbs free energy. But for a pure component, the partial molar Gibbs free energy is equal to the molar Gibbs free energy. So this one is G underbar. So I'm just going to write some parenthetical notes here for your own information of what I just said. Okay, so if I just rewrite this one a little bit neater, I've got partial molar Gibbs free energy is equal to molar Gibbs free energy plus RT ln of the mixture fugacity over the pure component fugacity, TPX. Now, in order to evaluate this expression or simplify it further, it does us no good to have mixture fugacity as a function of TP and X. We have to actually plug in what it actually is and what the fugacity is. So we can show, I'm not going to show you this derivation, but for an ideal solution, so we're going to do this for an ideal solution and for an ideal gas. Remember, the two are different. Ideal solution. This is the one where the interactions between the particles are the same as the interactions between particles of the same type. So interaction between molecules of different types are the same as molecules of different types. For the ideal solution, you could show that the partial molar Gibbs free energy of component I for the ideal solution is equal to GI plus RT ln of XI. So I'm not going to show you this derivation. It's not too long, but I don't think it's super important to know. Derived. So again, we'll skip the derivation. This is in section 11.3 in Dom and Visco. I'm really trying to give a good balance of showing you all the details, but not getting too bogged down in the details where you lose sight of how it's actually going to be useful. So I know today has been a little bit of derivation heavy, and it'll continue to be a little bit derivation heavy. Some steps I'll try and skip so we can get to the bigger picture a little bit faster. But really what I wanted to do was compare this expression for the ideal solution to our expression for partial molar Gibbs energy. So comparing the light blue equation to the green equation. And you see that the expression is exactly the same if I can say that Xi is equal to the partial molar fugacity divided by the pure component fugacity. And this is what is known as the Lewis-Randall rule. So leads to the Lewis-Randall rule. So these equations have to be equal. Therefore, we can say that Xi times Fi, so this is the mole fraction of component I, Fi is the pure component fugacity. This is equal to the mixture fugacity of component I. Also, don't lose track of the, I'm going to keep the subscripts. So F5TP is equal to the mixture fugacity T, P, and X. Mixture fugacity of component I. So if you think about this and try not to get lost in the maze of the symbols as thermodynamics frequently does, this makes a lot of sense, right? If I wanted to know what the mixture fugacity is, that is the fugacity of a component in a mixture, all I have to do is take whatever the pure component is, pure component fugacity, and then multiply it by the mole fraction. And that is for the ideal case only. And again, that makes a lot of sense because ideal oftentimes matches what our intuition says. So by analogy, and I'm going to skip a little bit of this and refer you to this same section 11.3 if you're interested in more details. For the ideal gas, where there are no interactions between the molecules anyway, we can do something similar and say that the Gibbs energy, partial molar Gibbs free energy of component I for the ideal gas. So differentiated in notation, ID is ideal solution, IG is ideal gas, is equal to GI IG plus RT ln YI. So Y again because it's a gas, it's a vapor phase, X because it's solution in a liquid phase. So we can say the same exact thing where we can say that the F hat, the mixture fugacity component I, function of TP and X, TP and Y over Fi, T, and P is equal to Yi. Now, since for an ideal gas, the fugacity is equal to pressure, I'm going to replace this by pressure. So for ideal gas, F equals P. Remember, we did that before the break as well. And therefore, we can say that the mixture fugacity of component I for an ideal gas, function of Tp and X, Tp and Y, is equal to the pressure times the mole fraction. So these are two important relationships. Again, these are for ideal cases. We've got the Lewis-Randall rule. And then this is not the Lewis-Randall rule. This is just an analogous relationship. In both cases, we can model what the mixture fugacity of the component I is for the ideal gas or the ideal solution. In the next video, which will be the last one today, we'll handle deviations from ideal behavior, which is frequently what we're interested in phase equilibrium.